Hello guys, welcome to my channel Physics Homework. Hope you all are alright and God bless you. In today's video I am going to discuss on the quantum hypothesis given by Max Planck and photoelectric effect which discovered by Einstein. So let's start it. The quantum hypothesis. The quantum hypothesis, first suggested by Max Planck in 1900, postulates that light energy can only be emitted and absorbed in discrete bundles called quanta. Planck came up with the idea when attempting the explain blackbody radiation, work that provided the foundation for his quantum theory. Planck found that the vibration energy of atoms in a solid is not continuous but has only discrete values. Light energy is determined by its frequency of vibration f. Energy E is described by equation E is equal to nhf, where n is the integer and h is the Planck constant, which is equal to 6.626 multiplied by 10 raised to minus 34 joule second. So here is our second topic, the photoelectric effect. So we have already mentioned the success of Planck hypothesis, which makes it appear that in the process of emission or absorption light behaves as if it were a particle-like bundle of energy. However, the evidence here for the quantum nature of energy exchange between radiation and matter is indirect. It was Einstein who drew the attention of the fact that the phenomenon of photoelectric emission could be understood in the terms of Planck's hypothesis and provides a direct verification of the hypothesis. This phenomenon is the emission of electrons by many metals, especially the alkali metals, and they irradiated by light. By applying Planck's hypothesis, Einstein proposed that absorption of light of frequency nu by electron in the metal takes place as discrete quanta of energy h nu. If h nu exists, the amount of energy W needed for an electron to escape from the surface of metal, the electron absorbing such quanta may escape with energy up to maximum value E max is equal to h nu minus W. Available experimental data were in conformity with this equation, which was accurately confirmed by later experiments. On the basis of classical theory of absorption of light, it would be practically impossible to understand that the existence of maximum electron energy related to the frequency nu of the incident radiation as well as absence of any photoelectric emission, the inability of electrons to acquire the amount of energy required to escape. Nu is below a definite value, V0 is equal to W by H. In the classical theory, there is no reason to expect any sensitive frequency dependence for the amount of energy which an electron in the metal could ultimately accumulate by gradual absorption from the incident light or rays. Nor can one see why there should be a definite upper limit of the energy so absorbed. Other properties of photoelectric emission are also equally difficult to understand on the classical picture, but are almost self-evident. When this phenomenon is viewed as the instantaneous absorption of light quanta by the electrons with which they collide. For example, photoelectric emissions start instantly when light falls on the emitter, however weak the light intensity may be. Casually, the electron would need some time to absorb enough energy to escape. Under irradiation with monochromatic light, the rate of emission of electrons is directly proportional to the light intensity, which is exactly what would be expected on the quantum picture since the number of quanta, and hence of the collision with electrons, is evidently proportional to the intensity of light. Conclude there without further discussion that in the photoelectric effect, light behaves as a collection of corpuscles and not as a wave. At the same time, we know only too well that the phenomenon of diffracted etc. require light to be a waves. How are we to escape the paradox created by existence of two quite irreconcilable manifestations? for one and the same physical entity? So here you can see the photoelectric effect. The photocurrent I depends on the intensity of light. Intensity given by energy by area cross time, and energy is equal to intensity cross area cross time. Energy is continuous for classical and energy is discrete for quantum, as we seen in the hypothesis of Planck. E is equal to nh nu. I is equal to nh nu by area cross time. It is proportional to I proportional to n by t. I proportional to nu. I proportional to A inverse, or we can say area inverse. Here we can see our third formula. E is equal to h nu, P is equal to E by C, and M is equal to h nu by C square, where P is equal to mc, which is mass cross speed of light. For particle nature, we can see here that phi is equal to work function, the minimum energy required to eject the electrons from the surface of a particular metal. So we can make one equation, h nu is equal to kinetic energy max plus phi, where phi is the work function, k is equal to kinetic energy, h nu is the energy of the quantum hypothesis by Planck. So if we need phi, which is equivalent to the threshold energy to eject our electrons from the metal, and where nu 0 is equal to c by lambda threshold. So here the lambda threshold, which is defined by the minimum threshold value of wavelength of light which is collided on our metal to eject our electron sufficiently. If our wave has no threshold value equal to lambda th, then it will not eject the electron from our metal. So if you want to eject the electrons from our metals, so you have to require to give the enough energy or enough wavelength of threshold value. So at the end we obtain that Ke max is equal to h minus nu 0. So here we can see that there is a two possible condition for our formula, where nu less than nu 0, Ke max is equal to given us minus negative value, not valid, there is no ejection of electron at this value. And in other condition, nu greater than or equal to nu 0, Ke max is greater than or equal to 0, which is possible to eject our electrons from our metal from that lambda threshold value of our wavelength of light. After the ejection of electron, if we want to detect the electron, there is a formula which is called ejection of electron, given by I is equal to dq by dt. As you can see here in the figure, for electron detection when current showing, then photoelectron is possible. Total K1 plus K2 is equal to Ke1 plus Ev. Here we can see I is equal to dq by dt, I is equal to E dne by dt, where q is equal to n, where we can see n is equal to small number of electrons per unit time. So we can write also for our photon. So I is equal to E dn ph by dt. So here our equation of intensity given by I is equal to nh nu by a cross t, n by t is equal to ia by hv. So at the end n by t is proportional to intensity. So our current also I proportional to intensity, hence the photocurrent is also depends on the intensity of light or wavelength of our light. And hence for kinetic energy max for no electron, when V is equal to minus 10 volt and I becomes 0. So induction of electrons from metals is indirectly or directly 0. So here is fourth formula for stopping potential. the absolute value of potential at which photocurrent is 0. As you can see here in the figure, the distance r, intensity I0 from the source which is collided on the metal, which is given by our formula I proportional to 1 upon r square. So indirectly I is proportional to I and I is proportional to 1 upon r square. As you can see, r is equal to distance between source and incident surface. If you want to increase the intensity value, then you have to decrease the value of r and vice versa, as you can see from our equation. So here is the graph of kinetic energy max on a y-axis versus the new frequency on the x-axis. Kinetic energy max is equal to h nu minus h nu 0. And here in the kinetic energy versus I, where you can see the voltage is constant, so our kinetic energy also constant with the increasing current. Here is our another graph, voltage and current at V is equal to constant and I is equal to constant. So here the value of V threshold should be V constant, so we can get our constant graph. And from our equation, I depends on n by t, where n is the number of electron and t is equal to time. Here we can see our another graph, voltage and current. Here we can obtain different current values for different threshold values, but it will become a constant with the increasing value of voltage V. So here we have our another graph, current and intensity, where we can see V1 is less than V2 and I is equal to constant, where constant is equal to number of electrons per time. So here we can see that Vs2 and Vs1 has started their threshold voltage value at different intensity, but it will become a constant intensity with increasing current. So here our last equation, incident radiation wavelength lambda 0, stopping potential nu 0, energy of incident photon hc by lambda 0. Ke is equal to EV, hc by lambda 0 is equal to Ke max plus phi. So E nu 0 is equal to hc by lambda 0 minus phi, where phi is equal to work function, h is equal to Planck constant, c is equal to speed of light, and lambda 0 is the threshold value of wavelength of our monochromatic light. So from this function we can obtain the energy of incident monochromatic light. So I end my discussion here and hope you understand my point clearly. If you have any doubts, then comment below your doubts and also subscribe this channel, and also you can follow my Instagram page Physics Homework 01. So until that, see you in my next video.